Hey everybody, welcome to part 2 of my AP Calculus Unit 4 review videos. Basically in the last video we talked about motion. In this video we'll talk about related rates, linearization, and L'Hopital's rule, so I hope you enjoy. Alright, so now we have a problem called related rates. There are different kinds of problems like these, but I'll give you an example. So here, a spherical balloon is filled with air at 8 inches cubed per second. How fast is the diameter of the balloon increasing when its volume is 36 pi inches cubed? So in these types of problems, they give you a lot of information, such as like rates and certain like actual numbers and stuff like that, and we have to relate them together, related rates. And that's how we're going to solve the problem. And you definitely have to do a bunch of these to get used to how it works. You're gonna need to know the volumes and surface areas of different shapes. So you have to actually know that. So that sucks. I have to memorize it, but it's how it is. So yeah, basically, let's actually just figure out our information. So we are trying to figure out the diameter of the balloon. So let's think about what we have. So it's a sphere, so that means it's going to be like the volume is going to be the volume of the sphere. So let's say volume. We know that it's going to be, well, if you remember the volume of the sphere, that's going to be 4/3 pi r cubed. All right, and we want to know how fast the diameter is increasing. Diameter is just 2 times the radius. So we can solve for the radius and multiply that by 2 to get the diameter. And then how fast we want to know how fast that's increasing when its volume is 36 pi inches cubed. So then we'll also have that. The volume, yeah, and this is going to be 36 pi. Okay, and then from here, we just basically find the rate. We want to find the rate of change of the volume. So what does this mean? So because it's being filled with air, so its volume is increasing at this rate, 8 inches cubed per second. So let's use that. So first, what is the derivative of the volume with respect to time? So let's see. So let's take ddt of our volume, which is 4/3 pi r cubed. And we can take this 4/3 pi out because it is just a constant, so it's going to be 4/3 pi times d over dt of r cubed. So again, we can just move this, we can just say 4/3 pi out front times, so the derivative, so note how we're not taking the derivative with respect of t with respect to t. This is r. So what we're going to say is that this is going to be, we're going to take the derivative like normal, so it's going to be 3r squared, but then we're going to have a dr over dt. So this is going to be 3r squared times the rate of change of our radius over time. If it was just like the derivative of a function of t with respect to t, this would technically be dt over dt, which is just 1, so there's really no point in writing that. But here we do have to write it, so it's dr over dt. And so yeah, that's just kind of how it works. These 3's cancel, so we can just do that. And so eventually we get that this is 4r squared dr over dt. This is our rate of change of our volume. This is dv over dt. And that's actually equal to 8. Okay, well this is good because we want dr over dt, right? Kind of. Well, we want the rate of change of the diameter with respect to t. So let's see. Let me make this note. So since r is just the diameter over 2, that's just the rate of the diameter over 2. Actually, let me call the diameter capital D. Okay, because I don't want to confuse it with our d's here with our derivative here. So we're going to call that d over 2. So then this is going to be, so dr over dt equals d of capital D over 2 over dt. And you can write that as d over dt of capital D over 2. And again, you can just factor out this 1/2 times the derivative of capital D over dt. So basically, if you have something here, you can move it out front here. Let me put parentheses around this. So for example, if I have like dy over dx, this is equal to d over dx of y. That's just how it works. You can just basically move it out front however you like. And so we just move this from here to here. And again, this is 1/2 times d, which we move the 1/2 out front, times the derivative of diameter with respect to time. So that's really important because we kind of needed the diameter, not the radius. So we can say that this is going to give us the implication, oops, let me make that arrow a little better. This gives us the implication that 4r squared, actually 4 times r over 2 squared, or d over 2 squared, times 1/2 d over dt equals 8. All right. So 2 squared is just 4. So this actually cancels with that thing there. So then so we get that this is d squared, and then we can multiply both sides by 2, so that we get this is d over dt. This is equal to 16. And what we want to isolate this, but we don't know what d is, capital D. So that's where this relationship comes in handy. So we know that this is, so again, we have 4/3 pi times d over 2 squared, d over 2 cubed actually, is equal to 36 pi. So we can rewrite this. So 2 cubed is 8. So we have 4 over 8, which is 1 over 2. So this is going to be 1 over 6. So we can just say pi over 6. So let's just verify. So 2 cubed is 8. So yeah, so it's going to be pi over 6. This 4/3 pi, and then times d cubed equals 36 pi. And then we can say that d cubed, we can cancel out these pi's. 6 times 36. Well, actually, we don't need to figure out what that is because 36 is 6 squared. So 6 squared times 6 is just going to be 6 cubed, so then d equals 6. So we can just plug that in. We need to say that this is d over dt is just equal to 16 over 6 squared. Over 36, basically. Since 6 squared is just 36. So then we can reduce this, and we say that the rate of change of the diameter with respect to time, so how fast the diameter is increasing, is just going to be, let's see, so let's reduce this. So 8 over, so 36 is just 15 plus 3, so yeah, 8 over 18, and then that reduces to 4 over 9, and that's all we can do. So 4 over 9, and this is going to be, so diameter, measure of that is going to be inches, but per second. Inches per second, because time is in seconds. Wait, is it second? Yeah, it is seconds. So this is how fast it is changing. I know this was probably a little confusing, how we did everything. Kind of with the diameter thing, I don't know if I probably should have included that. But okay, so let's kind of recap. So this is our velocity, or volume, sorry. This is our given information. This is me trying to find the derivative of the velocity, and I did that until here, and then we set that equal to 8, since that's how quickly it's changing. Here, this is where I'm converting our radius to our diameter, and we just get that this is 1/2 times the change of the diameter, and so this is where I plug the information in. And then obviously I had to figure out what our diameter was at this moment when it's equal to 36 pi. And then we plug all that information and get this answer here. It was a lot, but I wanted to show you an example of how related race works. So if you, you should definitely watch some other videos to get more used to it, and definitely do some practice problems, because just watching this is not going to help you. Alright, I think there are one or two more topics I want to go through, so let's do that pretty quickly. Alright, so we're going to be talking about linearization and L'Hopital's rule, so I'll talk about those in a second. Linearization is this first thing. So given that g of 2, which is a function g of 2, or a function g of x, at 2, it's equal to negative 4, and the slope is, at all points, is going to be the square root of x squared plus 5, approximate g of 1.95. So it doesn't give us the function g, and it's not like we can find it. I mean, we can if we know a little more calculus, but right now we cannot. So we're not going to actually find what g is. It's actually not going to help us. We want to approximate what g of 1.95 is. We know that g of 2 is negative 4, so it's going to be around negative 4, but we want to do a little bit better than that. And so what we can do is this process called linearization. And so let's think about it this way. If we know point slope form, it's y minus y1. In this case, y1 is this. Yeah, it's going to be y minus negative 4, which is y plus 4, equals a slope, and I'll talk about the slope in a second, times x minus 2 in this case. And you know, that's our point slope form. So what is the slope? So we can actually just plug in g prime of 2 into here. So g prime of 2, so we put, let's say, g prime of 2 is going to be equal to the square root of 2 squared plus 5. So the square root of 4 plus 5, which is square root of 9, which is just 3. So we just put 3 here. And that's cool. But now, if we want to approximate this, we just say 1.95 is equal to x. And then we just solve it from here. So let me just do it here. So y plus 4. Actually, let me isolate y. So y is equal to 3 times 1.95 minus 2 is going to be like negative 0.05. So yes, 3 times negative 0.05 plus 4. So then y is equal to negative 0.15 plus 4. So then y is just equal to 4 minus 0.15, which is going to be 3.85. And that's it. So that's how we approximate it. It's a really weird process, actually. It's actually nice how it works. And it actually kind of makes some sense. At least it should. This whole thing about plugging this x in, that's basically just our little difference in how our x's are between our x that we want to approximate versus the x that we know. So you just plug in the information. It's not too hard, and we get this as our output. Again, do more problems with these. It'll definitely help you. So now I want to talk about L'Hopital's rule, which is a rule that'll help us with limits. So we're going to revisit limits briefly, and basically, now that we know how to take derivatives, we can help whenever we solve limits. So if we try to solve this first limit, and don't be scared with the r, it's just a variable. So r cubed plus 2r minus 2, if we plug 1 in here, we get 1 plus 2 minus 2, I'm sorry. Yeah, we get that 1 plus 2, I'm sorry, this is supposed to be a minus 3. Yeah, minus 3. So 1 plus 2 minus 3 is just equal to 0, and then 1 squared minus 1, that's also equal to 0. We get 0 over 0. We can't have that as a limit. So if we take the derivative of this, so if we, what I like to do is do this and then put like a little ddr. This is going to be equal to the limit as r approaches 1 of, we just take the derivative of the top, which is 3r squared plus 2 over the derivative of the bottom, which is 2r. What the heck just happened? Basically, if we have a 0 over 0 situation, an infinity over infinity situation, then we can take the derivative of the top over the derivative of the bottom, not the quotient rule, just the derivative of the top over the derivative of the bottom, and then we can actually solve this. So the limit here is just going to be 3 plus 2, which is 5 over 2. That's it. That is our answer. And this is actually going to be equivalent to what we would have gotten if we actually like looked at a graph or something. Really cool thing. Now, if you get something over 0, or then you're not going to actually, this isn't going to work. If you're going to get 0 over something, that's just 0, so that you don't even need to do this. But if you get an actual answer, like if this was equal to like 5 over 2, if you actually knew that, then if you took the L'Hopital's rule, it wouldn't really, it might change the answer. So only do it if you get 0 over 0 or infinity over infinity. So let me actually put that over the side. So 0 over 0 or infinity over infinity. And it can be plus or minus, as long as they're the same, I believe. I think they could be different, but yeah. So here's the limit as x approaches 0 of sine x over x. Sine of 0 is just 0, so we get 0 over 0. So of course that doesn't work. So let's take the derivative with respect to x. And then we get that this is still the limit as x approaches 0 of sine of, so sine of x, the derivative of sine is just cosine. So cosine of x over 1. And the, cosine of 0 is just 1. That's it. So yeah, that's not too hard. And here, sometimes so actually, let's first rewrite this. This is the limit as x approaches infinity over x squared over e to the x, right? So I mean, you could tell that, okay, e to the x is much more powerful than x squared. But this is just a good another example for what I'm about to show. So we can actually take the derivative. And this gives us limit as x approaches infinity. Wait, let me make that x a little better. Of 2x over e to the x. This is still going to give us like 2 times infinity over e to the infinity, which is, again, infinity over infinity, like it would give us here. So let's take the derivative again. And yes, we can do this as many times as we want to actually get to our answer, as long as we actually get somewhere at some point. So we get that this is limit as x approaches infinity over 2 over e to the x. And now we can see that if we plug in infinity in the bottom, we get this is 2 over infinity, e to the infinity, which is 2 over infinity, which 2 over a really, really big number. It's just going to give us 0 at the end. And so that is L'Hopital's rule, derivative of the top over the bottom, only if we meet 0 over 0 or infinity over infinity. And then, of course, we have linearization. Check out all of these topics that we covered today. Go on YouTube or something, because I hopefully didn't confuse you a lot. I just wanted to get through this very quickly and not drag this video on much longer than it already is. So thank you all for watching, and I hope you can actually understand these topics, and again, do a lot more practice with them. Bye, guys.